Hello again. In this video, we're going to go over some examples where we evaluate definite integrals using geometry. Now at this point, we have two different ways of evaluating definite integrals. One way we can evaluate definite integrals is by appealing to the limit definition of the definite integral. But obviously this is a difficult way of finding definite integrals because it requires us to find a limit. The other way we can find definite integrals is by appealing to the geometric interpretation of a definite integral, which is that it's equal to the net area trapped between the function and the x-axis, starting at the lower limit and ending at the upper limit. And that's how we're going to evaluate definite integrals in this particular video. Now later on, when we get to section 5.3, we'll learn that there's actually another way to evaluate definite integrals using the fundamental theorem of calculus. But we'll talk about that in the next section. Okay, for now, we're going to evaluate definite integrals by appealing to its geometric interpretation. Okay, so let's look at this one. Let's find the definite integral from 2 to 4 of 2x plus 3. First of all, if you graph 2x plus 3, that's just a line with a slope of 2 and a y-intercept of 3. So its graph looks something like this. And what we need to do is we need to find the net area trapped between the function and the x-axis, starting at 2 and ending at 4. So in other words, the area in here. Well, this is just a trapezoid. And we have a formula for the area of a trapezoid. It's, first of all, this is the base of a trapezoid. And this side over here is called the height, or h1. This one is h2. So the area of a trapezoid is 1/2 the base times the quantity h1 plus h2. Okay, so the base, you can see, is 2 units long, right? 4 minus 2. Height over here, h1, you can find by plugging 2 into the function. Notice when you plug a 2 in, you get a 7 out. So that means this distance here must be 7 units long. So that's h1. Of course, h2, you could plug a 4 in to the function and you get an 11 out. So h2 must be 11. Okay, so again, using the formula for the area of a trapezoid, we get 1/2 the base times the quantity h1 plus h2, right? And if you calculate this, that ends up giving us 18. So this area in here is equal to 18, okay? Which is equal to the definite integral, right? Because that's equal to the net area trapped in here. Okay, so I think you can see that this is much easier than trying to evaluate the definite integral by appealing to its limit definition. Okay, so let's look at part B. Let's find the definite integral from 1 to 6 of 2x minus 6. Okay, again, 2x minus 6 is simply a line. It's got a slope of 2 and a y-intercept of -6. The graph looks something like this. And notice that the x-intercept is at 3, which kind of creates two triangles here. And we're supposed to find the net area trapped between the function and the x-axis, starting at 1 and ending at 6. Okay, so let's find the area of both of these triangles. So first of all, the area of a triangle is 1/2 base times height. So notice here, the base of this triangle is equal to 6 minus 3, which is 3. Then the height here we can find by plugging 6 into the function and getting the y value. So if you plug a 6 in, you get 12 minus 6, and so this would be equal to 6. Okay, so it's 1/2 the base, which is 3, times the height, which is 6. In other words, half of 18, which is 9. Now this is going to give us a positive contribution in the Riemann sum, right? Because the function is above the x-axis. Whereas this triangle down here, the area of this triangle is going to give us a negative number in the Riemann sum. Now, the area of this triangle obviously is not negative, but when you calculate this as a Riemann sum, you are going to get a negative number here. Okay, so let's find the area of this triangle, remembering, though, that this is going to give us a negative contribution since the function is below the x-axis here. Okay, so the base of this triangle would be 3 minus 1, which is 2. Then the height you can find by plugging 1 in to the function. You get negative 4. That's the reason we're going to get a negative contribution, because if you calculate this as a Riemann sum, then you're going to get negative y values out. Okay? But in terms of a distance, this distance would be equal to 4. Okay? If you wanted to find the area of this triangle, it would be 1/2 the base, which is 2, times the height, which is 4. And so half of 8 would be 4. So the area of this triangle is 4. But when you calculate this as a Riemann sum, this part here will give you a negative 4 as its contribution. And this will give you a positive 9. So you have to remember that this part here gives you a negative contribution. Okay, and so the net area that's trapped between the function and the x-axis, starting at 1 and ending at 6, is going to be 9 minus 4, which is 5. And that's equal to this definite integral. Again, we didn't have to use the limit definition to find it. We used the geometric interpretation of the definite integral, which is the idea that it's equal to the net area that's trapped between the function and the x-axis. Okay, let's look at one more. So let's find this definite integral from 3 to 4 of the square root of 1 minus the quantity x minus 3 squared. First of all, the graph of this function, the square root function, is a semicircle right here. One way of knowing that is if you start off with y is equal to this square root, and you square both sides of this, you'll end up with y squared is equal to 1 minus the square root of x minus 3 squared. Then if you add this x minus 3 squared to the other side, you're going to get x minus 3 squared plus y squared is equal to 1. That's the equation of a circle. It's a circle centered at the point 3, 0 with a radius of 1. Okay, 3, 0 is right here, so that's the center of your circle. And then if it has a radius of 1, the circle would look like this. Now, the graph is actually a semicircle, right? The graph of this square root is the upper part of the circle. Okay, and so we're trying to find the definite integral of this square root starting at 3 and ending at 4. So if you start at 3 and you end at 4, we're talking about finding the net area trapped in here, which, if you look at it, is actually 1/4 of the entire area of the circle. Okay, so let's find the area of this circle. And then if we take 1/4 of that area, that'll give us this area in here, and that's the definite integral that we're trying to find. Okay, so the area of a circle is pi r squared. The radius of this circle happens to be 1. So we get pi times 1 squared, which is just pi. Then we're going to take 1/4 of the area of the circle to get the area in this piece right here. That's going to give us 1/4 of pi. That's our definite integral. Okay, so again, I think you can see that if you could appeal to the geometric interpretation of the definite integral, which is that it's equal to the net area, that's much, much easier than appealing to the limit definition of the definite integral. And so in the cases where we can do that, it's much easier and it's much preferable to do it that way. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.